Everyone. Our speaker today is Javier Osca. Our speaker is Javier Osca. I think I can say that Javier is a home product or a local product. He studied here as at UIB, and then he did his master at IFISC and also his PhD at IFISC with the supervision of Rosa and myself. And after that, he went abroad for postdoc. He was in a first postdoc in Belgium, in Louvain, where at IMEC or IMEC,
in Louvain, because Louvain is the French one.
Louvain, okay. Where he stayed for a couple of years. And after that, he went for a second postdoc in Ireland, in Maynooth University. And now, since first of this year, he is back at UIB as assistant professor and also as researcher at IFISC. And I think he's going to tell us today about his work in his second postdoc at Maynooth. So welcome, and the floor is yours. Thank you.
As Joren said, my name is Javier Osca. I'm now working in University of the Balearic Islands since the 8th of January of this year. And I'm here also in the Institute for Cross-Disciplinary Physics and Complex Systems. I'm going to present today SOQCS, a library for stochastic optical quantum circuit simulator for the simulation of quantum optical circuits. I developed this work while working at Tyndall on behalf of Maynooth University. And the first thing you might ask to yourself is why quantum optics? What is quantum optics? So quantum optics are important as an alternative to perform quantum computation. As an alternative to perform quantum computation with superconducting qubits, because photons are the coherent frames. The coherent free are more resilient to noise and are easier to create and manipulate in large entangled states. And this paper that I have put here to you is the first paper that demonstrated that it was possible to do quantum computation with linear optics. Linear optics, that means that we can model the optical elements with matrix. But also is complementary to quantum computation with superconductor qubits, because with photonics we can connect classical and quantum machines, remote systems. Classical or quantum. So therefore, something that is being done today is that, for example, we can have various, well, remote is something relative, but we can have various machines based on superconductor qubits in a large room, and we can it's being studied the possibility to interconnect them with photonic circuits and fibers to have like a cluster of superconducting qubit quantum machines. So in this sense, quantum optics are important for quantum communications. For example, I put yourself here a paper. I can put many papers. I just selected a few that were important for me. Here a paper of qubit teleportation between neighboring nodes in a quantum network. Basically is how to teleport a quantum state to another quantum state that is a few nodes away. Similar this one, multi-qubit quantum logical gates, and also how it's possible to perform distributed quantum computing, because, for example, these heralded controlled nodes, the photons might be on different machines. Also, therefore, this kind of technology might be a building block for the quantum internet. And probably you already know, but this kind of technologies are also important for quantum cryptography and secure communications. And I also put a paper of an experiment to you in there. But then we need tools to design and test quantum optical circuits. And therefore, I have developed the tool that is SOQCS. SOQCS is a stochastic optical quantum circuit simulator that is a Python and C++ library to simulate optical circuits for quantum light modeled as Fock-wave packets. This is a relatively large library in the sense of it's around 15,000 lines approximately of C++ code, plus another 5,000 of Python. a few hundreds of C and maybe another few hundreds of scripts to perform installation on the library and things like that. But the first thing that we have to define, I have been told that this seminar is something that must be introductory at first, because not everybody here works even in quantum mechanics. So the first thing is, okay, but what is a quantum circuit? What do you understand as a quantum circuit? And here is my model. I understand as a quantum circuit like a series of optical elements interconnected between them by photon beam lines. These optical elements are linear optical elements. That means that we can represent them by a matrix. We can have also delays and lossy medium that cannot be represented easily by a matrix, but the library is programmed in a way that you can read them in the same footing from the side. A user can declare them in the same footing, but the library has to do some things internally to manage them. And we have emitters, we have detectors, and photons travels from left to right in this plot. In this sense, there is no resonances in the sense that the distance. I add this because I know there are people that comes from quantum transport, and there is no resonances. That means that the distances between optical elements are large, that the Wave-Packel length. Therefore, a photon that is traveling through here will find first one optical element. They will perform a quantum transformation, then another, and this is sequential. And photons cannot be reflected back to the circuit. So a photon cannot be arrived here, be reflected, and turn back. It's only from left to right, and different optical elements are applied sequentially. And SOQCS allow to build circuits from non-ideal optical elements. We will expand on that. We can define imperfect emitters. We can configure detectors. We can perform a simulation of the whole thing using different methods. And we can read and analyze the result at the end. There are some tools to this.
Rubén, perdona, tenemos pendiente pedirte un material a Storage y tengo que hacer el contrato menor. Y no encuentro presupuesto.
Okay, that's funny. First, I would like to present this very simple circuit with only 2 channels, with 2 photons, a beam splitter, a balanced beam splitter, and 2 detectors. This plot is generated automatically by SOQCS once you are declared the circuit in here. And basically, this beam splitter can be represented by a unitary matrix with 2 cosinus, 2 sinus that depend on theta, and 2 phases that depend on phi. And this matrix is represented at transformation by the constructor operators at the input and the constructor operators at the output, and perform these transformations. Photons are bosons. So what happens is we have n1 photons in one channel and n sub 2 photons in another channel. We have this expression, and then this is transformed. And if we want the final state, then basically we have to put here the power of the number of channels, of the number of photons on channel number 1, number of photons on channel number 2, and expand this expression. For example, 1 photon on the first channel and 3 on the second will be used cosinus and sinus, 1, 0, 0, 1. The opposite, 0, 1, will be sinus and cosinus. And if you, the interesting one, this is interesting one, the 1, 1, because you can see that if the beam splitter is balanced, then the probability of having the 1, 1 output is 0. So if we have in a balanced beam splitter 1 photon and 1 photon, that photon has half the probability to come out on the first channel, half the probability to come out in the second channel, but they will come out paired, both of them on the first channel or both of them on the second, but none, if the beam splitter is completely balanced, none in separated channels. This is the very well-known Hom-Mandel effect or Hom effect, and this is the basis for computation in using quantum optics. For example, we can represent single qubit operations using photonic circuits. For example, I want to comment you, I am putting a bit of the code of what I am doing. For example, this is a SOQCS result. just to you to get to it and see how it works. We can do, for example, a RX rotation or P half will be represented like a circuit like this one. And in SOQCS, we can simulate this little circuit. And then we can, for example, encode the result into a qubit, into a logical outcome. Well, how this is done? This is path encoding. This is only one qubit represented by two channels. If we put 0 photons in here and 1 photon in here, this is a logical 0. If we put 1 photon in here and 0 photons in here, this is a logical 1, and this is one qubit rotation. So we can put also airwise, RZ, and we can do it of any arbitrary angle too. So with a photonic circuit, we can do single qubit operations. That's not a big deal for the moment, but we can do more than that. One of the difficulties of working with linear optical circuits is that not every possible quantum operation can be represented with an optical circuit. We need always a small nonlinearity. And this can be solved in two ways. One way is to put a nonlinear term somewhere, but this is out of the scope of SOQCS. And another possibility is to do post-selection. That means a partial measurement at the end. How this works? Imagine this is a non-deterministic phase shift. That means that we put various phase splitters with certain parameters. We have here a phase shifter, and we want that we put in channel 0 the linear superposition of having 0 photons, 1 photon, or 2 photons. We want to change this phase. That's the operation that we want to do with this circuit. If a simulation is executed, then we will see that this looks nothing like this. So what is done is that two ancillas are added. We put two ancilla channels, sorry. We add a photon in here, and then we do a partial measurement of the output in here. We demand that this to be a 1 photon in here and a 0 photon in here. And this gate works, but 1/4 of the time. So it means that you read the output, do a partial measurement, it's a 1, 0, I keep the output. If it's not, I reject it. And experimentally, this is done. Basically, what is done is to repeat the operation many times and build the statistics afterwards. And doing that, when we do post-selection, we apply a projector, then we obtain the proper state that we were searching for in the remaining channel, non-post-selected channel. Note that in this example, for example, we are defining photons, and we are declaring the post-selection condition in the detectors. We are not speaking about mathematical properties like projectors or states. And this is basically because this kind of things are treated internally by SOQCS, but they are presented in a more nice way for the user. With this gate that is called NS gate, we can build large circuits. In SOQCS allows using one circuit to work as a gate for a large circuit. So, and we can define the circuit that, so this comes from this famous paper of Neil Lama and Milburn that I commented before. And basically it's a control phase flip. Basically we have a 0, 0 that is encoded as 0, 1, 0, 1, a 0, 1 that is encoded as 0, 1, 1, 0. The first qubit is channel 0 and channel 1. Second qubit, channel 2 and 3. The channels 1 and 3 are not painted. 2 is the draw, the plot, but will be a line that will go for will enter in optical element throughout the circuit. And this is 0, 0, 0, 1, 1, 0, 1, 1. And basically we see that the 1, 1, the phase is shifted. We can see here that are the ancillas used by the gates and the detectors used from this gate too. Another interesting gate is this one. This is, for example, a CNOT, but this is a bit different than the previous one. In this CNOT, basically, we are not looking at a phase change, so we can we are only interested on the probabilities. If the input is 0, 0, the output is 0, 0. But if the input is 1, 0, the output is 1, 1. We can plot because we can plot. In this case, we are interested on the probabilities, and if we can instead of the amplitudes of probabilities. So when we have real numbers, we can plot it. So this is the probability distribution. In this case, it's very trivial because there is only one possible outcomes. but we can plot it in SOQCS probability distributions. And in this case, it's not normalized to 1. You cannot see it because it's very little. But this is normalized to 1/9. 1 fraction 9 is 0.11, because the normalization is indicating the probability of success of this gate, but can be normalized to 1 if you want. And you have a series. We have two ancilla channels initialized to 0 or no photon in here. These are the qubit gates, and we post-select to 0 and 0 in these gates. So one funny thing of this gate is that the photonic output will be this one. Will be 1 0 1 0. That is the one we are searching for. But we will have a 1 1 0 0. That means 2 photons in the first qubit and 0 photons in the other. This is something that cannot be encoded into a logical representation. Therefore, when we encode it, we reject this output. Basically, it's like an additional post-selection condition. So we are demanding 0 photons in this channel, 0 photon in these channels. Otherwise, we say that the gate has not worked. But we are also demanding only 1 photon by qubit. Otherwise, we also consider that the gate has not worked, and we reject the output. In this particular case, that means that this gate cannot be stacked. For a case to create large circuits. In this particular case, in the previous gate, we can do it, but in this one, we cannot do it. And yes, yeah, probability discussion, yes. So at this point, you are wondering maybe how this is calculated, how this magic works. No? So one possible way to do it is directly as we will do it by hand. We have the operators at the input, we have the occupation at the input, and just expand the expression, and we do it like we do it on hand. So with a bunch of coefficients that depend on where the photon is on the input, and the possible permutation, and the possibilities at the output. Of course, this is very costly. This scales very poorly. It has a computational cost of n over n factorial, that is like saying exponential. This is a very bad, nobody uses that kind of algorithm nowadays. I have to be honest, I only included it in SOQCS because when I was building the library, I need something easy to actually test that the whole library is working correctly, and then to develop and later on to focus on other methods. However, I found it out that even if it scales poorly, it's a bit better than it looks at the beginning, because when these operations have a very low cost in actual real clock time, and very easy to optimize. If one of these is 0, everything is 0. So you can stop the calculation very early if something is 0. That makes that for very few photons, 4 or less than 4, 4 or less than 4, this is a bit faster than the other methods. And this is relevant because many experiments are in 4 or less photons. The most of the experiments, if not all, are 4 or less photons. So this is more useful than it looks. Then basically there are other methods that are based in calculation of permanence, basically to calculate which is the amplitude for every possible gate at the output of a state. A state has many gates, and each gate has an amplitude. For each amplitude, a permanence has to be calculated. That has many rows. It's a square matrix. A permanent of a square matrix, and that square matrix has as many rows and as many columns as photons. This scales as and a permanent is like a determinant, but instead of having 2 signs, positive and negative, we have only positive signs. And this little difference is very important because there are no super efficient methods to calculate permanence numerically. Basically, there are 2 formulas. This one, the Bala-Subramanian-Bax-Franklin formula, and the Reiser formula. This one has a nicer scaling that is not good, but better than the direct method. Is the order of n by 2 elevated to n. And this one is better between 4 and 10 photons. And this one, the Reiser one, is good for arithmetic. In other words, both of them, the permanent calculation scale the same for both formulas, but this one is a bit better for smaller matrices, and this one is a bit better for larger ones. And furthermore, this one I found out a recent paper of London and Markstrom that they discovered how to calculate permanence using the Reiser formula with parallelism, in a way that the calculation of that permanent can be parallelized in various cores of the computer. So that makes for this, of course, this only compensates if your matrix is relatively large. But it's very good because you have 10 cores on your computer, 12 cores, something that nowadays is easy to find out. You can go 10 times faster, for example. Not 10, but a bit more faster. And so it's another optimization that we have with the Reiser formula. Which one? Yeah, I don't know very well the mathematics behind it. So I know that I follow the numerical recipe. This is very well known from textbook, and there are numerical recipes to actually perform this kind of computations. But I'm not a mathematician myself, so I cannot enter in those details. Yeah, there are some benchmarks that I produce using my laptop. For example, this is the time to calculate a single amplitude with the direct and glean method. Balasubramanian glean method means the Balasubramanian Bax Franklin glean for 2, 4, 6, 8 photons until 30, and for a random circuit with 4, 8 double channels and photons. And as you can see, basically this grows very fast, 1 to 10 photons, and basically the gleam does not grow that fast. So it's more or less the same time to calculate a glean amplitude with 22 photons that with the direct method with only 10. We have here a comparison with also single amplitude, but with more photons for the glean and the Reiser formula. And as you can see, when the number of photons is large, the matrix is large, and the Reiser it performs a bit better for large matrices. And here, this one is Reiser with multiple cores, in particular 10 cores. I can configure the number of cores I want to use, but I use 10. So and you can see it's not a factor 10 of improvement, but it's a good improvement from 62 milliseconds to 14, 86 to 14. So this is very good as benchmarks, but they are not real life cases. In real life, we don't want to calculate only one amplitude. We want to calculate the full state, that is the full amplitude distribution. So we can check. We want to check all the possible output and check if the amplitude is 0 or non-zero, and it's non-zero, which is the value of the complex amplitude. So for 2, 3, 4, more realistically, we will be working at most with 7, 8, 9, 10 photons. That depends on some other condition, but between 7 and 10 photons will be the realistic circuits that we can handle. So double channels again, random circuits, and we have here direct, glean, Reiser, and Reiser with 10 cores, and we can compare. We can see how glean performs a bit better for smaller matrices than Reiser, and how for these small matrices the parallelism does not have that much value, but as soon as we start increasing the number of photons, parallelism becomes more important, and Reiser begins to be a better method. In this sense, yes, you can see that for each one, direct F, we have direct R. For glean F, we have glean R. What that means? Here we calculate the full distribution, but the R is what I call restricted distribution. What that means? If we are working with logical circuits that has a logical interpretation, that means we are doing pattern coding. So it's going to be at most, we are intending to have at most 1 photon by channel. And if we are doing polarization encoding, that means qubit 0 will be horizontally polarized, and qubit 1 is vertically polarized. It's also at most 1 photon by channel. So we can restrict, instead of checking every possible output, we only check those that has at most 1 photon by channel. So we have to check less possibilities, and therefore it's faster. And furthermore, if in this case it does not apply because it's just a random circuit without post-selection, but if we have post-selection, we don't need we know in advance that we are going to reject everything that is not cannot be post-selected. So we can only check for those outputs that we know that they are going to have some chance to be, at least are going to go through the post-selection process if we are not interested in intermediate state. We'll receive more distribution, the number of outputs that we have to check, and makes the overall algorithm also faster. So there are many optimization possibilities in here. I don't know how we go on time. Oh. I have explained the exact methods, but there are also the possibility of having sampling methods. What is a sampling method? A sampling method is we ask for a method and generate a list of possible outcomes. So basically, how this is done. If you want to know which is the probability distribution of the output, this is not good method for it because you have to calculate many permanents to actually have enough. You need a very large sample, many outputs, and to calculate the statistics from it, which usually is not very efficient. But the reason because these algorithms are important is because they're important in the context of quantum supremacy. There are people that there is a heavy discussion about comparing a quantum optical circuit, a real one, or a quantum computer with a circuit, a random circuit, with the output of a random circuit simulated in a classical computer, which is faster. One might think that the quantum computer is going to be faster because a quantum process in a quantum computer is native, but there are many things to discuss about it, and people are doing this kind of comparison. What characteristics or what parameter has to have a real quantum computer to be faster than a classical one in his own game and demonstrate the quantum supremacy. So in discussion of how many time these algorithms spend to create a sample compared to how many times a quantum computer will take to make the same operation, that is important. And people use this kind of algorithms to discuss it. So one very classical algorithm is one classical paper, sorry, is this paper of Clifford. And the Clifford algorithm that is goes with the 3 to the power of m, and n is the number of photons, L the number of channels, and basically works in this way. We have n photons, each one are different channels. We put the first photon with certain probability in a certain channel, calculating a distribution of amplitude of a distribution of probabilities for the first photon. Then, provided that the first photon is in one particular channel, we calculate the second, and so on and so on. So we need the calculation of many amplitudes of probability to have only one sample, one outcome. And the Clifford B that scales with n 2 over n is the same basic algorithm. It's just that for calculating each one of these probabilities, instead of calculating the permanent calculations are split in the permanence of calculations various smaller matrix and the time compensators. This Clifford B is not yet implemented in SOQCS because I need to understand a little bit of the properties of these smaller matrices to do it, and I have to sit down with Cam to do it. But instead, I have another Metropolis algorithm from Neville, published on Nature on 2017, that basically is a sample, is an accept with a probability acceptation and rejection algorithm, in the sense that given that we have a sample S, an outcome S, we propose an S prime, and with certain probability we accept or not that outcome. This is the probability of sample S, and this is the probability of sample S prime, and these PCs are the classical probabilities ordered in samples, assuming that these photons are distinguishable particles. And this because we propose a new sample with not with only 4 probability, with the classical probability to be obtained in that circuit. Because these are circuits that are have more channels than photons, therefore collisions are supposed to happen, but in a low number. Collisions mean that you have more than one photon by channel at the output. And we can also do that in SOQCS. We can ask for an outcomes in a sample, plot the probability distributions, or we can ask for the sample itself and plot it ourselves with pandas or whatever, you know. So, okay, this is okay for ideal circuits, but we have spoken about imperfections. So what mean imperfections? For example, we have spoke about a balanced beam splitter. Two photons are completely indistinguishable. Two completely synchronized photons are going into a beam splitter are indistinguishable. So we have a 1, 1, and then we have a 2, 0, and 0, 2. But we can assume that maybe what happens if these two photons have like two characters. We can distinguish them somehow. They are completely distinguishable. For example, they are very far apart, one from each other. So their wave functions do not overlap. So we need, or they have a very different frequency. So we have the blue photon and the red photon. So basically, what we have is we have a 25% probability to have the output in any of the possible, and we have the same probability for any possible outcome. So, and how we represent this? We add extra degrees of freedom that we call packet degrees of freedom, and we say if these photons are completely distinguishable or completely distinguishable. If they are on the same, they have the same, in each channel they have the same character, they are indistinguishable, and they have opposite, they are completely distinguishable. But what happens if they are partially distinguishable? And how this can happen? They are synchronized, but more or less. They are more or less the same frequency, more or less the same time, but not perfectly. No? Their wave functions overlap, but it's not a perfect overlapping. How we handle that? So in this sense, I follow what was proposed in this paper of Malte-Tiki, that is basically perform Gram-Schmidt orthonormalization of the packets. And therefore, we start for two partially overlapping packets. And after orthonormalization, we have perfectly that our photons are in, or are perfect, are in a linear superposition of perfectly overlapping packets or perfectly orthogonal packets in a way that adding extra degrees of freedom to the channels works. And we can use, and this is very important because we can now use all the algorithms that we have present for ideal circuits for indistinguishable photons can be used with partial distinguishable photons, and we can put partially distinguishable photons in our program, and then select which is the algorithm that we want, including sampling algorithms, and that will work. So this is fitting. In this sense, as you will notice, SOQCS has no new algorithm inside. I based my work in previous works, but what is new is putting all those algorithms together to work together because they were not designed to work together. And in an easy way, as you can see, here this circuit is 3 photons. It's a beam splitter with 3 photons in each channel, and I can put the parameters that I want, internally library configures everything, and we can reproduce Malte-Tiki results, for example. And this, for example, is the probability of having the output, the orange one, 10 photons in, sorry, this is for 3, but this simulation is for 10 photons in one channel, 0 in the other, or 5 and 5 will be the purple one and everything in between. So the new thing here is putting everything together to make it work together and make it transparent to use to an user, because an user will not speak about packets or wave functions. We only configure the parameters of the photon, maybe frequency, time, and the width of the frequency and time where you can find the photon. We can also have delays. We spoke about delays, but delays are not a linear optical elements. How we deal with delays? So we consider that we split the time into periods that we consider very far apart from each other. We have one period and one period, and we will have a bunch of packets that partially overlap with each other. And this configuration of packets is repeated periodically. So, and these ones do not overlap between them, but do not overlap between periods. So we have some packets in here with some coefficients, and we have some other packets with some other coefficients with a bit of overlapping between them. But if the relative overlapping between them is the same, these coefficients will be the same in here, than in here, in here, than in here. Therefore, moving a photon from one period to another. That is what a delay will do. It's simply a relabeling. For example, we can start the overlapping. We can start putting two packets in here. Only one of them. We can define two-way packets in here, but only one of them only one photon will be initialized to this way packet. Same two-way packets in here, but only one photon will be here. These two photons are completely distinguishable because they are different periods and they do not overlap. However, if we change the label from this to this one, then we know they are partially overlapping, and we know that these coefficients are the same. So we only have to to make this transformation. You only have to change the label because the relative coefficients will be the same. And this delay allows to do things simple and as complicated. I very much this circuit because it looks very simple and very innocent. Only two beam splitters, a filter of polarization and a rotation, and looks very simple, but it has everything. We have. In this case, I will explain, it has an emission of quantum dots with entangled photons that will be not perfect. It contains a delay in here. It contains post-selection and period filtering. How this works? Basically, two entangled photons will be emitted by an emitter, and later on, another two will be emitted. The first two photons, one will go through this channel. One will be speeding here. So there is a probability that goes from this delay and will be delayed. Then two additional entangled photons are emitted, and one of them goes here, and there is a possibility that goes through the filter. Yes, and basically this one and the larger one will interfere at the beam splitter, and if the post-selection is fulfilled, the entanglement between these two is transferred. The state that is created and defining here will be teleported to one of the photons in here. But this is a 3-photon protocol, but 4 photons are emitted, so one has to be ignored. Furthermore, the post-selection only happens for photons that interfere at a particular time or in a particular period. So the detectors has to be configured to only select photons, only be open for detections at a particular period, and ignore the rest. And it's something that can also be configured easily with SOQCS. As you can see here, we have detectors in channel 0 and 1. One photon is the post-selection condition. Does not matter the polarization. And here we are selecting which period will be listening, Basically, we obtain here the corresponding density matrix that is equivalent to the analytical. This circuit has an analytical solution, and is one of the circuits that used to validate SOQCS. So we can reproduce that analytical result. Okay. But we have spoken about matrix, and I have called a stochastic quantum optical circuit simulator, but I have not seen until this moment anything stochastic. So why the name and why the density matrix? How? Basically, this is the first circuit that I model with SOQCS. Therefore, the stochastics, you will understand in a minute why I say stochastic. Basically, it's a very simple entanglement swapping protocol where we have a quantum dot that emits at 2 different periods, two photons. One photon that comes from Byers-Seaton, a Byers-Seaton to a cascade. The first photon comes from a Byers-Seaton, the second photon from a Byers-Seaton, and the same at some other time. These two photons are entangled. These two photons are entangled. This photon is delayed. Then this photon and this photon arrive both simultaneously at this beam splitter. There is post-selection, and this entanglement and this entanglement is swapped to an entanglement between these two photons. So this is theory. But what happens on practice? We would like to have an emission that is horizontal, linearly superposed to vertical, being horizontally polarized and vertically polarized, first photon and second photon. But what happens on practice is that if you are emitting a cascade of 2 horizontally polarized photons and 2 vertically polarized photons, there is a little bit of difference in energy that leads to a phase accumulation. So the density matrix of that emission will be not 1, 1, but it depends on a phase. Furthermore, we can have some dephasing and having still correlation, but not linear superposition because of some effect. And we might have noise because some scattering event on the quantum dot, or maybe noise of the circuit. So the overall density matrix will be the sum of this density matrix with the probability of each of the events to happen by certain scattering probability, the phasing probability, noise probability, and so on. So basically, what we do, what SOQCS can do is only work with pure states. So what we're doing here, and where the stochastics come from, this density matrix is equivalent to an stochastic process in the sense that we emit with certain probability this state. This is a decision tree. Okay, we start here, launch a coin. Certain probability we go through the root. Certain probability we go through this another route. With this probability we emit this. With probability we emit this. So we choose probability in a stochastic way which one of the states the emitter will emit. Then the simulation is performed, and we store the result. This is performed many times until we have enough statistics, and we are storing this in a density matrix on a class that in an object we call the density matrix that stores the output states. And we have many. We can say to that class of the C++, calculate from all those states the density matrix, and can calculate it and can print it. And here's from where the stochastics come from, the name of the library, because this is the first problem that I solved with this library. And there is a stochastic process in the way that the emitter emits the different states. So, and you can believe me, this result, that is a density matrix, is also equivalent for a particular set of parameters to the analytical results, because the simple case has also an analytical solution. And you can see here we have the 4 possibilities: horizontal, vertical, horizontal, and vertical, and channel 0, and 02, 02, 20, and 02. That is, these numbers in parentheses are the packet number 0 and packet number 2, are referring to these 2 photons, which is first and which is second, basically. Once we are here, please allow me to become a bit technical. A quantum photonic state can be represented like a list of tuples of complex amplitudes and vectors are vectors of occupations. So the probability distribution is the same, just that instead of having amplitudes, we have real numbers, probabilities. And basically this is everything that state has to know. Each level will be a combination of 3 quantum numbers. That will be the channel, the polarization, but also the wave packet. Because now you know that we have, because partial distinguishability, not all photons are going to be synchronized. So this is what, and this will be stored in the circuit. To have this photon abstraction that I have spoken about, we will define a stack of software where we define at the top one, we define photons. I want to put that photon in that channel with certain parameters. Okay. So what the photon layer will do, we'll create an state with a photon in certain channel and certain level, and we'll create a packet definition, and we'll send that packet definition to the circuit. Internally in the packet layer, the circuit will store all the packet definition in a table and perform some operation to be sure that there are no repeated packets, and so on. So then packets can be in SOQCS, can be a simulation can be configured to use all Gaussian packets or all exponential packets. With that shape, the shape model can calculate an overlapping matrix, and finally that overlapping matrix can be calculated use the Gram-Schmidt coefficients, the resulting matrix multiplied by the circuit matrix, and have the partially distinguishable photons. That means that the quantum circuit will be more that a circuit of matrix that is built by a multiplication of the matrix of each of the individual optical elements. We will have also a dictionary to relate the channel polarization and packets with the level. We have a detector definition with the polarization conditions. will contain white packet information, a lot of information, no? And we have here a structure, no? We have we want photons, we have a circuit with detectors, with packets and state, everything to create that ideal photon. How this goes on practice? This is how SOQCS is built. We have at the bottom the external agency library to manage matrix. We have an utility library with some support, mathematical support to perform Gram-Schmidt orthonormalization and handle dictionaries. We have states, we have circuits, we have devices with the photon extraction, probability bins to calculate probability distributions, density matrix, a simulation with the calculation method. And this is for multi-threading, but it's different from this one. I haven't spoken on how we can use various cores to calculate permanence. This is one thing, but sometimes you have few photons. Calculating permanence with multiple cores is not from a computer point of view, is not worthy. But you may want to calculate a density matrix, and that means to calculate the output of many states, and each of the states, each of the simulation is independent of the others. So at a job level, we can calculate the density matrix, creating outputs of states in blocks of 10. We can simulate 10, then another 10, another 10 in parallel. So, and this part of the library is what provides support for that. We have here, this is all C++, but we have a Python interface with Python in a way that we can write. In fact, everything I have shown you today is Python. I have not shown you how this works internally in C++. This is very good because this means C++ is faster than Python. So SOQCS is fast, but has a Python interface. So it's easy to use too. And you can use the plotting libraries that we like from Python. And basically, I have not spoken too much about detectors. I have basically detectors is more than just post-selection. We can configure the detectors for post-selection, but depending on the detector configuration, we can calculate the output probability distribution. And we can compute also dark counts. There are some realistic effects that can be added to the detectors. We can add some dark counts. Dark counts are, for example, the detector has a temperature, so there is a possibility that by the temperature that the detector has, emit a photon and detects the photon that the detector has itself emitted. So these are called dark counts. And there is follow a Poisson distribution that can be included into the output. So you can calculate the thermal, you can include the thermal effects into your output. Compute the time. Basically, the time is if a photon arrives, the detector is blind for some moment. The model of calculating this in SOQCS is not that complicated. What we do is simple. The detector has a probability to be off, and this is it. And then we have the filter measurement window that we have spoken about. We can calculate the post-selection. We can also remove the degrees of freedom depending on the detector definition. We have spoke about packets. What happens if photons are partially distinguishable or distinguishable and array with different packets? But at the end, the user might say, okay, this is very nice to calculate which is the right output, but I only need to know how many photons by channel because I'm doing an experiment. And at the end is what I detect, how many photons by channel. So basically, we perform here the integration to give that result to the user. And here we can add noise. For example, let's see the home effect. You have that in your scale, your home effect is something like that. But this is wide enough to be seen experimentally, or you have a source of white noise that is going to make that feature not possible to be seen. So you can add noise for your output, and this way check if what you are calculating will be visible or not, if you know how much noise you are going to have in your experiment. And this is, for example, again, the home effect, one photon each channel, and basically different effects that I have spoken about being added to obtain the final result. This is the ideal, and this is after those classical effects are computed. And this will be the final result. Something, and this is the finish. We have also a small, very simple model of losses, and it will be more than 2 minutes, and I finish. We have a pin splitter model of losses. What that means? A pin splitter model of losses means that everything that is not transmitted, that means that it's lost. So we can say, okay, we have a device like this one that is a dielectric that have two channels with two outputs and has losses. And everything that is not transmitted by one of the channels, that means that is lost. So I consider a device like the whole device like a beam splitter, where part of the photons go to the physical channels, are physical solutions that I can measure, and other part of the photons go to fictitious channels that just go out of the system and are where the losses are computed. So in a way that you can make a calculation like if no losses were present. And this is the Barnett-Loudon model of 98. And basically, this is a non-unitary matrix. TNR, I have not put it, but T square, R square is not one. This is a non-unitary matrix. We can perform single value decomposition. And from a non-unitary matrix, and this matrix obtained from single value decomposition, an unitary matrix, because the whole circuit, the losses, la de transmitted plus lost photons has to be represented by a unitary matrix. We obtain that big matrix has double the degrees of freedom that this one, and is unique except for row and column interchanges. And with this procedure, we can simulate and reobtain what this classical paper obtained. We can reproduce the same results, and it's basically, for example, we have a 2-0 input. This is the probability in black. I cannot see it. Okay, this blue is probability to have a 1-1 output. The yellow is a 0-2 output, or the probability to have no output. Will be either transmission is 0. You will have one probability of not having any output. But if the transmission is 1, then basically you have 0 probability of not having a 0 output. And basically you can calculate all these probabilities this way. And now the difficult part is saying, okay, this is for one particular dielectric thin film, but what happens when you have a full circuit made of many linear optical elements? That's what the approximation, we are using an approximation here. We use a model in which the whole optical circuit behaves like a single device, like the dielectric thin film. And under the assumption that the loss of photons, the photon loss do not return to the circuit, losses are independent, and this very big one, this is a big simplification assumption that is not completely true in real life, but is the assumption that we use for this model. We assume that the effect of losses will be restricted to a loss of amplitude. Therefore, if I input a pure state, my output is also a pure state, but with a normalization and amplitude that is not 1. So this is an assumption, and we build the total circuit multiplying by linear optical elements like phase shifter like elements, but where the transmission probability is not 1. So we multiply a non-unitary matrix by a non-unitary matrix to obtain a non-unitary matrix, and then we extend it in the same way that we have explained here. And basically, SOQCS is, as a summary, SOQCS is a Python and C++ library to simulate imperfect optical circuits for quantum light. You can find, I don't know if we have internet in here, but you can have the manual for this library. You can find it in here. It includes building circuits from individual optical elements, post-selection as part of the definition, partial disintegration of photons, losses, physical emitters, physical detectors, various simulation cores, some analysis tools like probability distributions and systematics, a Python port, and you can check. From this library, we have also 2 publications. And thank you very much.
There any comments or questions?
Just a curiosity. Did you get any feedback from users so far, or what is the type of feedback that you are getting?
For the moment, not a lot of feedback, to be honest. But yes, I have some people that have occasionally that will be that they are working with it. Basically, the most feedback that they have get is people that want different emitters, different emitter models, and a way to add more easily emitter models into the library.
I had a comment about experiments. You didn't mention much about experiments. Is there the purpose to compare with?
Yes. But
experiments?
basically, I was attached to an experimental group when I was developing this. And basically, the idea was was kind of a broader idea to have some. The idea was to we have some tool where we can design the circuit and check different effects to see if what are the reasons because the experiment goes that way. So yes, it's kind of a bit of a general model, but the idea was to include imperfections, partial distinguishability losses, realistic emitters and detectors, to say, okay, you have an experiment on the table, ideal experiment that you know what you are going to obtain, but you do this on practice, what you can expect to obtain, and is there any problem with that? There is no problem, those kind of things. Yes, the idea was to use this as a sync tool that experimentalists can check that the sync is robust, for example, as many other things. Well, that depends on what you ask, because post-selection, you are adding post-selection restrict how many outputs. For example, if you only want one single amplitude, you can go as far as 50 photons. But if you only want one single amplitude. But if you want a full distribution, maybe 8 photons is realistic. And if you are adding post-selection conditions, I have pushed the algorithm to 12 or 14 photons. But many of them are going post-selected. Therefore, the output distribution that I'm checking is smaller. So there's a bit of things to do. But let's say 8, 9 is realistic.
Any question from our Zoom attendants? If not, we can stop here. Thank you again.
Sí, clica para allá, que creo que se me va.
Sí. Oh, esto está grabando, hay que parar que deje de grabar.
Sí.
Bueno,
Pero sigue grabando.
por aquí había algo, ¿no?